Hello class, today I'm going to show you another application of explicit dynamics, and I'm going to use a little bit more options we have to show you what are the possibilities. Okay, this time I'm not going to start from the beginning, so I'm just going to show you what I've done for this simulation and then show you the results. So let's see what are the materials I selected. I selected concrete 35 megapascal one and structural steel, which is the default material. For the geometry, I used SolidWorks to draw a wheel and a base for it. The material for the ground is going to be concrete and the wheel structural steel. So let's see this one. This is our wheel, and I created this base as a ground for the wheel to roll over it. And if you want to import some geometries from other softwares, basically you go to assembly, click file and import it. And then you can come here and edit it. For example, the base for my drawing wasn't thick enough, so I brought it here and then I clicked pull and select this part and dragged it to have a bit thicker base for my simulation. So you have a lot of options here. So these are the geometry we had. Let's open model and check the mechanics. Okay, so these are the geometries, and based on the colors you can see the green one is the concrete base and the gray one is structural steel. So what is the plan? I decided to assign a very high velocity to this wheel and see what is going to happen when it's rolling over this base and ground. So let's check if I assign material for these. So this is concrete, this is structural steel, so we're happy with the geometry. With the mesh I already did, it's not very fine. I should have much finer mesh, about like the top half of the space, and even for the outer surface of the wheel, and for the area we had sharp edge. But yeah, this is good enough for our video. And then for the initial condition, I wanted to use velocity and angular velocity both. So I selected velocity for this wheel at the direction of x axis, positive x axis, and the magnitude of this velocity is 50 meters per second. So it's a good velocity and it's high velocity. And then just because I wanted to use angular velocity for this simulation, I added angular velocity. So this wheel is going to rotate clockwise with 200 radian per second angular velocity. And you know, if you multiply angular velocity with the radius of this wheel, you can get velocity, which is going to be about 60 something, because the radius is 32, 35, something like that. So if you multiply 200 with 0.31, you are going to get about 60. And you need to add that velocity to the the other velocity, which is 50, so the overall velocity is going to be 115 meter per second. And in terms of kilometer per hour, if this was a car, the car is supposed to go 415 kilometer per hour. So it's really high speed. So if this wheel, which is structural steel, is going to move very fast with 400 kilometer per hour velocity, I expect to have a failure at the top side of this concrete because of this high velocity. And to make everything much more clear, I asked ANSYS, whenever you had a failure of any element, just remove it. And how I assign that? Inside analysis settings, you go down for erosion controls and you turn on material failure, and it is yes now. So whenever the elements for the concrete reach to yield stress, they are going to disappear, which in reality it is going to be something like that. When the concrete parts start breaking, they're not going to tolerate anything, so they're going to be dust, so it's like a disappearing. Okay, so I added angular velocity and linear velocity. Let's check the analysis setting. We are going to simulate 0.004 second, and it's going to be our end time. I added standard gravity G at negative y direction, as you can see, negative y direction, and you can add it from inertial. And because I wanted this wheel to always sit on the ground because of the gravity, otherwise it could just move horizontally without any movement. So if this wheel start digging inside this base, it is going to go down lower and lower. So let's see. And then I created a fixed support at the bottom to keep it fixed as a ground and nothing else. Then I added equivalent stress, equivalent strain, deformation problem, velocity for this wheel to see what is the overall velocity or directional velocity. Let's see the result. This is our stress. Let me first watch it perpendicularly. And okay, this is good. Now let's move to the results I have. I already selected 100 result outputs, so and I could check this to 10 seconds. Let's see. Yeah, see, these red dots are the disappearing elements, which are the failured elements. ANSYS is getting rid of them, and as you can see, when they are disappearing because of the gravity, wheel is going inside the ground and our base. Consider this is a 400 km per hour speed, so it's just digging it. And if I pause it, the maximum stress is about here. Let me change the unit to see in terms of megapascal. It's 800 megapascal. It's definitely failure here for the structure still, but I just wanted to show you the effect of this high speed and how it is going to destroy elements and dig. So later you need to improve this design. Definitely we're not designing any car for 400 km. So let's watch it with this angle. Mostly the maximum stress is about the center, which is we have very thin layer of structure still there. Okay, the next information or solution I asked was strain, which is going to be similar. Let's see. Okay, deformation probe. I selected deformation for the top side, the top surface. So the green one is going to no deformation, and then when we have a deformation based on the highest deformation, gradually this deformation is going to increase. As you can see, it's a millimeter and gradually increases as time passes. Because of this high speed, we are having a large deformation for the concrete, and this wheel is digging and destroying a lot of elements here. Okay, and finally I selected velocity probe for the whole wheel. The result I'm looking for is a total velocity. Let's see what's the total velocity, and then we can see the directional one. So we can see here, let me drag this a little bit higher. Velocity, the total velocity gradually decreases as wheel gets in and digs more inside the this ground. But it's about let me change the unit, meter. So it's about 115, the total velocity. Let's check the directional. For example, in X direction, it would be interesting. Yeah. So as this wheel digs inside, so we are going to have vertical component of velocity. So when we have vertical component of velocity, the overall velocity is stable. It's about 115, but because of presence of the vertical one, the horizontal one is going to get smaller. So that is why the horizontal velocity, the overall horizontal velocity is lower, and it's about 110. So 5 meter per second decrease because of this digging. And you can see the velocity change during this simulation. Okay, so we learned something here. We can use linear velocity and angular velocity and check how the geometries can deal with each other in explicit dynamics. One idea would be using this angular velocity. For example, I was thinking, instead of this simulation, I could simulate a blade to rotate and assign like angular velocities like 200 something radian per second, and then put it over a surface, like a base surface like this, and then move that blade from left side to the left side to the right side, and that moving action is going to cut some material from this surface, and it's like going to be like a milling operation. So if you were interested, do that milling operation using angular velocity and horizontal displacement over a surface. The surface you are supposed to cut should be a bit softer, and the blade or milling tool should be a bit stiffer to be able to cut the surface and have like a flat surface. It's just idea. If you had the time, do it. It is going to be interesting. Okay, thank you very much. Enjoy